In this video, I'm going to show the math of what would happen if you were to detonate the Tsar Bomba toward the bottom of the Mariana Trench. I think it's easy to imagine that you'd end up with worldwide tsunamis and or earthquakes and or volcanic eruptions, but it would just cause a huge underwater cavitation, so I'm going to show the math on that. This is interesting because I'm going to keep this on a real basic level with just some high school algebra and a little bit of introductory calc and introductory physics, but I'm starting from the very basics on those and building up. So hopefully if you just have some high school algebra skills, you'd be able to follow along and understand this. But I try to keep my videos on a real simple level so that almost anybody can understand them. First up, I'm just going to show how to derive the units here for newtons and for joules, since I'll be working with both of those in this video. Wikipedia gives a little bit different of a definition than what I'm used to for joules, so I just went through the derivation right here, first to get newtons, then to get the joules, and then I combine some stuff, but I won't go over it because it's right there. Next up, here's the basic logic. Once I realized that bombs are measured in energy, which is in joules typically, and all a joule is a measurement of force times distance, then I can use the energy of any bomb to calculate how far out the radius would be of a spherical underwater cavitation from a bomb detonation. So here's the graph here. You got your distance, you got your force. You take the integral of your force right here to get the area under the curve. When you multiply force times distance, you get energy, which is typically measured in joules. In this case, we won't have a distance of that underwater cavitation. We won't have a distance of that radius. But I will calculate the force of the water pressure. And we will have the energy of the Tsar Bomba, and that'll be the area under the curve right here. Go ahead and draw that out right here. So this is the energy. Force times distance is energy. If this was a rectangle, you would just simply take the y-axis times the x-axis. But since it's not a rectangle, we have to do an integral. I did a couple of videos on integrals already. One was to show just how to use them, and it's super easy, so you can see that if you want. In another video, I derived a proof of it, so that one's a little more detailed. But what we got here, since force times distance gives us the energy, we've got our bomb right here detonating underwater, and we're just going to pretend this will be a perfect sphere just for the ease of calculation, even though the bottom of this underwater cavitation will have a lot more water pressure than the top, so I would suspect it'll be asymmetric. But if you imagine, say, a jack here simply just pushing up, and right here we have water pressure pushing in on our cavitation right there, and we have a jack here pushing up against that, so we have the force times the distance. But as this cavitation bubble gets larger and larger, it requires more and more force, because in this thought experiment you'd have to have more and more jacks. Every time it gets larger, you're adding another panel, so you'll have to add another jack to push that up. So in this case here, this is how we get our increasing distance and our increasing force. The formula for total force will just be pressure times area equals the force total. The units will look like this: newtons per square meter times square meter for the area. The square meters will cancel. You'll just be left with newtons for a total force. Here's a way to visualize how pressure times area will equal your total force. Say you have 10 panels here around this sphere, and each panel has 10 newtons of force on it. So you have 10 newtons of force per panel. Say it's a square meter panel, and then you have 10 of those panels, so you'll have 100 newtons of force total. And if you were to take all 10 of those panels and either stack them up and put them on a scale to weigh them, or lay them out side by side to weigh them, you would get 100 total newtons of force. We have to get this total force here because it's force times distance gives us our energy, and that energy will be supplied by a underwater bomb. Next up will be water pressure. I'll start out with the imperial units here, since a lot of people know that the Challenger Deep, which is the deepest part of the Mariana Trench, is almost 7 miles deep. It's like 6.6 or 6.7 miles or something. So let's just say we're going to detonate our nuke 6 miles deep, set up our conversion equations so all the appropriate units cancel out. 6 miles, 1 mile is 1.61 kilometers, 1 kilometer is 1,000 meters, 1 meter is 100 centimeters, 1 cubic centimeter is 1 gram, 1,000 grams is a kilogram, then 1 kilogram is 9.8 newtons. Notice what happens here to all of our units. They should all cancel appropriately. Mile divided by mile, kilometers, meters. I got centimeter here and cubic centimeter here. So notice this centimeter will cancel. We'll be left with square centimeters right here for an area. And then grams will cancel, kilograms cancel. We're left with newtons. So we'll be left with newtons per square centimeter. And we got that square centimeter right here from the density of water, which is 1 gram per cubic centimeter. And so this is the way I did it. There's other ways to calculate water pressure, but for me, it's just easiest to remember. There's almost no memorization that water is 1 gram per cubic centimeter. So I just use that for my density for the equations. So now I have 9,500 newtons per square centimeter, but I want to turn that into square meters. So let's take our big square meter right here. This will be made up of 100 centimeters going this way, 100 centimeters going that way. So 0.01 meters that direction, and to the right and up. So it'll be 0.01 meters squared. That means I can replace this centimeter squared right here with 0.01 meters squared. Divide that by that, you get 9.5 times 10 to the 7th newtons per square meter. That'll be the force against which we'll be pushing when that bomb explodes in that underwater cavitation. And remember, energy is just force times distance. So now we have a force. We'll also have the energy from the Tsar Bomba. So now we just have to calculate distance. Next up, if we're pushing two things apart right here with a certain amount of force, I'll call the entire length here the diameter, and then half that length will be the radius. We have to use the radius to get the area of the sphere. 4 pi r squared gives us the area. But now if we have these two carts here, and I just showed some flames here pushing out to give an equal amount of thrust. So 1 newton of force or thrust pushing in for each one. And we have a jack here where we have to push them apart. The diameter right here will be 10, the radius will be 5. So for example, if all these carts are lined up here in a circle like this, then we're looking at the radius. To figure out the total amount of energy that we needed to push for a radius of 5, we don't use the radius, we have to use the whole diameter. So even though radius is 5 meters, so it's 1 newton times 10 meters gives us 10 joules of energy, which means we've used half the energy to push this cart to the right and half the energy to push that cart to the left. So right here, force times distance is your energy, force times diameter will equal your energy. And then that also means force times 2 times the radius will equal your energy. Thus, we bring the two under energy. We have force times radius equals 1/2 energy. So what this means is when we're comparing radius to the amount of energy, we actually have to cut our energy in half, because half of that energy is going to go to one side of the radius, the other half will go to the other. And I'll show how to use that here in the next minute or two. Also, I know the idea of having to cut your energy in half when dealing with the radius of a sphere. That whole idea can be a little abstract, so here's a way to think of it to make it look really simple. Imagine your sphere right here is made up of a bunch of panels, and you have a jack separating panels on opposite sides. So there'll be a whole bunch of jacks here in the middle of your sphere holding out panels. And as you crank that jack, then you're opening up those panels. You could actually take all those panels of that sphere, line up half of them on the right, line up the other half on the left, line up all your jacks in a row right here. Then you can see that each jack would look like this jack right here that's pushing apart these two carts. So if we want to look at the energy of something, say the energy of a bomb, and we want to determine what the radius is that that energy will be able to push out on those on the outside of that sphere, we actually have to cut that energy in half right there, because half of that energy has to go to pushing the cart on the right out, and the other half of the energy has to go to pushing the cart on the left out. So if we're measuring energy in terms of radius, we have to cut our energy in half. But if we're measuring it in terms of diameter, we could just leave it the way it is. But we have to use the radius because the area of a sphere is 4 pi r squared. Okay, Tsar Bomba energy, 2 times 10 to the 17th joules. And I know that's correct because I got it off the internet. So we draw out our graph right here, x and y axis. X will be the distance that we have to push out, which will be the radius of our underwater cavitation. This will be our total force right here, which will be pressure times area. The area will be 4 pi r squared. That's the area of our sphere. 9.5 times 10 to the 7th newtons per square meter is the water pressure pushing in. Notice how these units will cancel out here. We have a square meter. I wrote kind of small here, sorry. We have a square meter right here in the denominator, 1 in the numerator. This meter right here is also squared because it's radius squared. So what we'll just be left with is newtons, which is our total force. So the y column, or the y-axis, will be total force. The x-axis will be our distance, which is the radius in meters. Force times distance equals our energy. That equals 2 times 10 to the 17th joules. So what we can do here, even though we have what looks like 3 variables, we have our radius in meters, we have our force right here, which is in newtons on the y-axis. Then we also have our energy, which will be the area under a curve. By taking an integral, we just take an integral of the y-axis here, which will go out from some radius to 0. 4 pi r squared is the surface area times the water pressure. Again, notice that square meters will cancel out. Times, actually that's it. We're just doing the y-axis, so we just have the area times the water pressure, and then you write dr right here, which I wrote kind of sloppy, to show that we're only interested in the taking an integral of the radius right there. That equals our energy, but remember we have to cut that energy in half, because half the energy will expand out the radius to the right, and the other half will expand it to the left. Also notice for energy, we need to have Newton meters, and notice right here we're not going to get Newton meters in this current form. We have meters squared right here, and we have newtons per meter squared. So this meter squared and that meter squared will cancel. We'll just be left with newtons, which actually is a force and not an energy. But watch what happens when we take an integral. What we can do is just pull everything outside of the integral sign right here, except for the r squared, and then dr, and that equals our energy. By the way, I cut the energy in half. Instead of 2 times 10 to the 17th, I'm just calling this 10 to the 17th now, for the aforementioned reasons. Now we take the integral, which just means we raise the exponent from 2 to 3, bring it down to the denominator. We got 1/3 r to the 3rd. Now let's look and see what happens to our units right here. We have a meter squared in the denominator and a meter cubed in the numerator. So that meter squared will cancel. We're left with meter up here. Now we've got Newton meters, which is a measure of joules. I just wrote that here. Units go to equal Newton meters, which equals a joule. Go ahead and just solve for your r. We end up with 630 meters for the radius. And this was the Tsar Bomba in the bottom of the Challenger Deep of the Mariana Trench. So you can use any depth of water. You can use any bomb with the calculations I showed. And I know I'm mixing imperial and metric units here, but you can imagine if this is going off 6 miles deep and you're only getting a cavitation radius of about 6 or 7 football fields. If you were up floating on the surface, you wouldn't even know anything was happening below you. And I imagine that would be so deep also, you wouldn't even feel any warm water rushing up, because that water would have to go through, any warm water would have to go through 6 miles of cold water to get to you. Also, some more trivia. Energy drops off according to the square of the distance, because the area of a sphere is 4 pi r squared, which means if you're 4 times the distance, you will receive 1/16 of the energy. So it works the same way with sound waves as well. That's how sound drops off. So yeah, you'd be so high. If you were floating up on the surface, you'd be so high and so far away from this. I'm thinking you may not even know what was going on below you.